Okay, so what do we mean by a rational function? So recall from last year when we did functions, a rational function is some polynomial p of x divided by some polynomial q of x. So some polynomial, quadratic, cubic, whatever, divided by some other polynomial, again, quadratic, cubic, whatever. So this top is a polynomial. Okay, and the bottom is also some polynomial. Okay, so it can be very general, but just some polynomial divided by some polynomial. We call that a rational function, and we want to integrate this. So we want to find the integral of p of x over q of x dx. Okay, for example, we might have something like this, where we have the integral of 2x squared minus 1 over 1 minus 3x plus x cubed. Okay, something like this. Now, in this case, you might be able to do a u substitution. If you let u be the bottom, the derivative might be the top. But in most cases, that can't be done, and we need to try something else. Okay, and what we're going to do is a partial fraction decomposition. A complicated sounding thing, but it's quite straightforward. So we will do a partial fraction decomposition to simplify the function. In order to integrate. So what we're going to do is take this complicated function and split it up into a sum of terms where each term is a lot easier to integrate. So as a whole, like this is very difficult to integrate. But once we split it up into the sum of terms, we'll see each one is very easy to integrate. And then we can just add up all the answers. Okay, we get our total result. Okay, so the way we do this is in 4 cases. Okay, so there are 4 cases to look at. Okay, so again, depending on what rational function you're given, we can use one of these 4 cases to simplify. Okay, so the first case, case number 1, is when we have p of x over q of x. So we've got our rational function is equal to some polynomial, again, p of x. So the numerator can be anything, that doesn't matter. But the bottom, we can factor into a product of linear terms. So we end up with ax plus b, cx plus d, and so on. Okay. So the top, that's some polynomial. We're not interested in that. But this denominator, we can factor into some linear terms. Okay. For example, we can have 1 over x squared minus 1. Okay, so in the bottom, we've got a quadratic, but that can be factored. So we can factor this as 1 over x plus 1, x minus 1. Okay, so we've got something at the top. We're not interested in that for now. But in the bottom, whatever that polynomial is, we can factor it. Okay, and we've got 1 factor, 2 factors, 3 factors, however many factors we get. So in the bottom here, we have a product of distinct linear factors. Okay, like we have in this example, x plus 1, x minus 1, those are the 2 factors for that denominator. Okay, so that's case 1. We'll see what to do for these cases now. So given this, so we have p of x over ax plus b, cx plus d, and so on. What we're going to do is split this up into a number of terms. And each one is much simpler than what's given. So this is going to be equal to some number a over the first factor. Okay. A, we don't know what it is. We'll find that out later. So it's going to be a over the first factor, b over the second factor. Again, a, b, c, all of those are just numbers. So b over the second factor, and then so on. Okay, so each linear factor in the bottom, that becomes its own term in the sum. Now, if you wanted to integrate this, that's difficult. But these ones, this, and this, these integrate to the natural log, because it's 1 over x. So we see that this one that's given can be very complicated looking, but once we split it up, integrating that, we just get the natural log. We know it already. You can just write down the answer. Okay, so that's case 1. That's the easiest one. Okay, case 2 gets a bit more complicated. So here we have, again, some polynomial p of x. Okay, it can be anything. We're not worried about that now. Over q of x. Okay, now if we can write it like this, okay, so we have p of x over, for this one, some of those terms here, these terms here, can be repeated. So if we have ax plus b and another ax plus b, that will be ax plus b squared. So if we have any repeated terms, we can write it like this. Ax plus b to the n. Right? If we've got 2 of them, then it's squared. If we've got 3 of them, it's cubed, however many. So we've got some number of them repeated, and then the rest are just like we had in case 1. So then the rest will be cx plus d, and so on. The rest stay the same. So one of those factors is repeated some number of times. So you might have x plus 1 squared. We got 2 of them, so we count it as repeated. So here we have a product of linear factors where some are repeated. Okay, and again, when I say it's repeated, think of something like ax plus b, then another ax plus b. We can write that as ax plus b squared. So there's 2 of them, so in that case, n will be 2. It's repeated twice. Okay, so what do we do in this case? So what we want is to write this as individual terms in the sum, but we need to handle that case of it being repeated. Now, when it's repeated, we do the following. So instead of just having one term like this, one term like that, we're going to have n terms for each repetition. So here we have ax plus b to the n. We're going to repeat that n times in the following way. So we're going to have a1 over ax plus b. That's the first one. Then it's going to be plus a2 ax plus b squared. That's for the second one. And this is repeated n times. So we continue this process n times. So this will be plus dot 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 plus an over ax plus b to the n. Okay. So we're going to have n copies of that first term, the ax plus b. But for each copy, we increase the exponents. So for the first one, it's just ax plus b like we had in case 1. But if it repeats n times, we need to add a copy with it being squared. We add a copy with it being cubed, all the way up to the last copy where it's to the power n. So if it's cubed, we're going to have 3 terms: the linear term, the quadratic term, the cubic term. If it's ax plus b squared, we're going to have the linear term, ax plus b, plus ax plus b squared. So the number of terms you have is always however many times it's repeated. If it's ax plus b to the 4, you have 4 terms. If it's ax plus b to the 3, you have 3 terms. And it follows the same pattern. And then for the remaining linear terms, it's exactly what we did for case 1. So all of this is for the first part. And then we still have cx plus d. We just carry on with what we did with case 1. So that will be b over cx plus d plus, and then we do the same thing. So the only new thing here is the first n terms. That is to take care of the n repetitions we have of ax plus b. Okay, so let's have a look at an example. Okay, let's say we have x cubed minus x plus 1 for the numerator. Again, for all of these cases, the numerator can be anything. We're not interested in that. It's only the denominator. So this is going to be divided by x squared, x minus 1 cubed. Okay, so let's see how many repetitions we have. Here we have x, it's repeated twice. Here we have x minus 1, it's repeated 3 times. So for this one, we're going to have 2 terms. For this one, we're going to have 3 terms. So let's do that. So this is going to be equal to, we're going to have a1 over x and a2 over x squared. Yeah. So a1 over x, but it's repeated twice. So now we need a2 over x squared. And we're done because it's only repeated twice. Plus, now we have x minus 1 cubed. That's repeated 3 times, so we need 3 terms. So we're going to have b1 over x minus 1, b2 over x minus 1 squared, because that's the second term. And then again, it's repeated 3 times, so we need a b3 over x minus 1, x minus 1 cubed. Okay, 3 times repeated, 3 terms. Okay, case 3 is when we have p of x over q of x is equal to sum p of x. Again, numerator, not interested. But in the denominator, instead of having a linear term, like the other 2 cases, we now have a quadratic term. So this will be ax squared plus bx plus c. Followed by something else, we know how to deal with that already. Yes. So this quadratic term cannot be factored. Okay, so in the previous example with case 1, we had x squared minus 1. That was a quadratic, but we could factor it into 2 parts. For this case 3, we have a quadratic, but it cannot be factored. Okay, think of like x squared plus 1. You cannot factor that into ax plus b, cx plus d. It cannot be factored. So we leave it as x squared plus 1, and then that will be case 3. So again, just make a note. This quadratic term, whatever it might be, cannot be factored. If it can be factored, then we just go back to case 1. If it can't be factored, we go to case 3. Okay, so that's how you differentiate between the 2. If you've got some quadratic and you can factor it, you go to case 1. If you've got a quadratic that can't be factored, you go to case 3. Okay, so what do we do in this case? Okay, so in the previous cases, these numerators here have just been numbers. So if it's a linear base, linear denominator like this, then it's just some number. Like that, linear denominator, just some number. If it's a quadratic denominator, then the numerator we make linear. So in the top, we're going to have ax plus b now over the quadratic. So that will be ax squared plus bx plus c. Okay, so for the linear factors, we had constant numerators. For quadratic denominators, we have linear numerators. And the pattern continues like that, but we won't look at anything beyond this. Okay, this is enough. plus dot dot dots. The other terms, we know how to deal with that. Okay, let's have a look at an example. Okay, so let's say we have x over x minus 2, x squared plus 1, and x squared plus 4. Okay, so let's see what we got, and we'll see what cases need to be used. So the first term, x minus 2, that's the linear one. So that's case 1. X squared plus 1 is quadratic. We can't factor it, so that's case 3. X squared plus 4 is quadratic. We can't factor it, so that's case 3. So we're going to split it up into a case 1 term, case 3 term, and another case 3 term. Okay, so for the first one, it's linear, so we're going to have some number a over x minus 2. The next one is quadratic. We can't factor it, so it's going to be some bx plus c over x squared plus 1. And the last term, x squared plus 4, it's quadratic. We can't factor it, so there's going to be some dx plus e over x squared plus 4. Okay, so again, the linear term, we just have a number at the top. So a over x minus 2, x squared plus 1, it's quadratic. We can't factor it. So linear bx plus c for the top. And then the last one, x squared plus 4, it's quadratic. We can't factor it. So some linear dx plus e at the top. Yeah, and that's the pattern we use. Okay, and then lastly, case 4. We have some polynomial p of x over q of x. Okay, this is going to be equal to p of x. Again, the numerator can be anything. We're not too worried about that for now. Divided by. Now, in the previous case, we had a single quadratic. Now, for case 4, we're looking at quadratics that are repeated. Like before, we had the linear case, and then the linear ones that are repeated. We have the quadratic case, and now the quadratic ones that are repeated. So here we have some ax squared plus bx plus c to the n. So we got some number of repetitions there. And some other terms, we know how to deal with that. Okay. But we're only interested in this repeated quadratic part. Okay, so what is this going to be? Well, it's the same idea we had with the linear one. Okay, so in the linear case, if we just go back up here, we had a1 over the linear term, a2 over the linear term squared, a3 over the linear term cubed. We're going to have the same thing. So we're going to have a1x plus b1. Because remember, it's quadratic, so the top has to be linear, over ax squared plus bx plus c. So that's the first repetition. Now we have the one for it being squared. So plus a2x plus b2 over ax squared plus bx plus c, all of that squared, plus dot dot dot, all the way up to the nth power, because we have n of them. So that will be anx plus bn all over ax squared plus bx plus c to the n. Okay, so that handles all of the repeated terms. And then we're going to have plus everything else for the other terms in the denominator. So that will be case 1, 2, or 3, depending on what's given. Okay, so let's have a look at an example. Okay, we've got x cubed plus x squared plus 1 all over x minus 1, x squared plus x plus 1, x squared plus 1, cubed. Okay, so let's see what we've got. Okay, x over here. This is just linear, so that's just case 1. We know how to deal with that. X minus 1, that's just case 1. We know how to deal with that. X squared plus x plus 1. Can this be factored? No, so that's case 3. We know how to deal with it. X squared plus 1. Can this be factored? No. Okay. And it's repeated. Okay, so this is case 4. So it's case 1, case 1, case 3, case 4. And we just add everything up. So the first one is just an x by itself, so that will be a over x. The next one is x minus 1 by itself, so that will be b over x minus 1. The next one is a quadratic. It cannot be factored, so it's going to be some cx plus d over x squared plus x plus 1. Plus, now that last one is repeated 3 times, so we're going to have 3 terms for that x squared plus 1. So let's write that here. So we're going to have, let's say, ex plus f over x squared plus 1. So that's for the first one. Now we need number 2. So it will be plus ef, let's say gh, so gx plus h over x squared plus 1 squared. That's the second one. Now we need one more because it's cubed. So that will be plus ix plus j over x squared plus 1 cubed. So we got the first one, second one, and third one because it's repeated 3 times. Okay, you could extend this to cubics, okay, but we won't be doing that. Okay, so we will only go up to repeated quadratics. Okay, anything after that, it can be done, so you just follow the same pattern, but you won't be tested on that. Okay. So this case 4 here, that is as difficult as it's going to get. Won't be anything more than that. Okay. Now we need to put a big star here. Okay, so all of this only works if the degree of the numerator is less than the degree of the denominator. So a big star there. The degree of p must be less, not less than or equal to, must be less than the degree of the denominator. Okay, you cannot do any of the above working unless the degree of the numerator is less than the degree of the denominator. You have to check that first. So you must check this before doing anything else. Okay, if you do not check this and you try to do this process, you're going to get rubbish. Okay, it's not going to work out. So whatever the degree of P and Q are, you must check this first. If this is satisfied, you can continue like we did in these examples. If this is not true, then we need to do polynomial long division. So I spoke a bit about this on the Thursday. I hope you all did your homework with the long division. Okay, everyone do that? Okay, so let's have a look. Okay, if this is not true, then we need to do polynomial long division first. Okay, so please make sure you check that before doing anything. Okay, so what is polynomial long division? So what we want to do is to take some polynomial p of x over q of x. Okay, so think of this just like a fraction, like 5 over 3, some fraction. So what we want to do is write this as like some whole number part. So let's call that f of x, some whole number part to this, plus some remainder. Remainder. Okay. So this polynomial long division, that's going to give us this whole number part, the f of x, and whatever the remainder is. So for example, like I said, that 5 over 3, we can write this 5 at the top as 3 plus 2. So this will be 1. The 3 over 3, that'll just be a 1 plus 2/3. So we've got this whole number part, the 1, remainder 2. Okay, so if we have 5 divided by 3, the answer is 1, remainder 2. And then the remainder we can write as 2 over 3, because that's what we're dividing by. So this is the idea of what we want to do. We want to take something like this, like an improper fraction, where the degree of the numerator is larger or equal to the denominator. We want to get this whole fraction, whole number part, like 1, and some remainder left over. That remainder left over, we then look at cases 1, 2, 3, or 4. Yeah, so let's have a look at an example. Number 1, we've got x cubed plus x over x minus 1. So we see the degree of the numerator is 3. The degree of the denominator is 1. Okay, that's not right. We want the top to be less than the bottom. So we need to do the long division. And like I spoke about on Thursday, we set it up exactly the same as if we were dividing numbers. Okay, but here we're dividing polynomials. So we set up the long division like this. So x cubed. We don't have any x squared terms, so we can leave a space there. So nothing there. And then we have an x. Okay. So this is like your hundreds, tens, and units sort of thing. What we want to do is divide by x minus 1. So we put that here. Okay. Exactly the same setup as if you were to do it with numbers. And we go through the same process. How many times does that go into there? Put it at the top, and then, times, and then continue. Okay. So we go through it. How many times does the x go into x squared? X cubed. So that'll be x squared. Right? Because x cubed divided by x is x squared. It's like we're doing this first bit. So ignore the number, that's not important. X cubed over x is x squared. And what do we do next? We take this, multiply by this, and put it here. Okay. So if you didn't do the homework or you forgot how to do the long division, please just make a note on the side of the steps. Okay, so we've got that. X squared times x minus 1. That's going to be x cubed minus x squared. And then we subtract them. And then we continue the process. So x cubed minus x cubed, that's a 0. You can put a 0 or you can leave it blank. Then we have 0 minus x squared. That's going to be x squared. And then we do the carry. Everyone remember the carry? Yeah, good. And we do the process again. X squared divided by x. That's going to be an x left over there. And then we multiply. So x times x minus 1. That's going to be x squared minus x. Then we subtract them. X squared minus x squared, you can put a 0 or you can leave it blank. And then we have x minus x. So that's going to be 2x. And we do the process again. 2x divided by x, that's going to be a 2. 2 times x minus 1, that's going to be 2x minus 2. Okay, there's nothing to carry down because it's just plus 0. But if you want to put a plus 0 and then carry that down, it's the same thing. Okay, but there's nothing there. And then we do it again. 2x minus 2 divided by the x. Subtract. So that will be 2. So we get 2 divided by that. We stop there. Okay. Because 2 has a degree less than x. You can't divide it anymore. You can do x squared divided by x. You can do x divided by x. But 2, you can't. You stop there. Okay, so that's going to be our remainder. So this top part, all of this is the whole number part. And the leftover, because you can't divide anymore, so we leave that. That is the remainder part. So let's put it all together. So we have x cubed plus x over x minus 1 is going to be that whole number part again. That's all the stuff at the top there. So that's x squared plus x plus 2. And then we have remainder 2. And what did we want to do for that last step? We wanted 2 divided by x minus 1. That would have been the next step. So this will be plus 2 over x minus 1. But we leave it at that because this degree here is 0. This degree here is 1. The degree of the top is less than the degree of the bottom, so we stop there. Okay, so again, this is like your whole number part. And this is your remainder. Now, in this case, the remainder is just 2 over x minus 1. That's easy to work with. We don't have to do any more work on that. Other times, you might have to do additional work. Okay, but here, that's fine. Let's do another example. Okay, I think after 2 examples, you should understand. Again, the method is exactly the same as what you did in grade 3 or 4 with the numbers, but here we just have polynomials. Okay, but the steps are exactly the same. So we've got x to the 4 minus 2x squared plus 4x plus 1 divided by x cubed minus x squared minus x plus 1. Okay, so before we look at any cases or anything like that, we look at the degree of the numerator, 4. The degree of the denominator, that's 3. 4 is larger than 3, so we have to do polynomial long division. So let's do that. Okay, we're going to have x to the 4. The x cubed term is missing, so that's like if you had your hundreds missing. You just put the 0. So that's missing, so we'll just leave a blank there. Then we have minus 2x squared plus 4x plus 1. Again, I just left the blank there. That's like the 0 in your hundreds, tens, units, whatever. Okay, we're dividing by x cubed minus x squared minus x plus 1. Okay, and we go through the steps. So x to the 4 divided by x cubed, that's x. And then we multiply. So that's going to be x to the 4 minus x cubed minus x squared plus x. Okay, and again, there's a plus 0 there, but we're not going to write that. Minus. Okay, let's take the difference. X to the 4 minus x to the 4, that should be a 0, but we can just leave it out. Then we have 0 minus x cubed, so that's x cubed. Okay, minus 2x squared, minus x squared, so that's a minus x squared. Okay, 4x minus x, so that's plus 3x. Okay, and then a 1 minus 0, that's just a 1. Okay, so that's step 1 done. We've done one step of that, and we do it again. So x cubed divided by x cubed, that's 1. And then we multiply. So 1 times that, we're just going to rewrite it. So that's going to be x cubed minus x squared minus x plus 1. And we subtract that. X cubed minus x cubed. Okay, x cubed minus x cubed, that goes away. Minus x squared minus x squared, that goes away. 3x minus x, that's a plus, so there will be 4x. And 1 minus 1, that goes away. Okay, now we see that this degree is 1. That other degree is 3. 1 is less than 3, so we stop there. So we have our whole number parts at the top, and we've got the remainder at the bottom. Okay, so this rational function is equal to x plus 1. Okay, that's our whole number parts. And then the remainder is 4x. So it's going to be plus 4x over whatever we were dividing by. So that was x cubed minus x squared minus x plus 1. Now, if we wanted to integrate this, then this part is easy to do. It's fine. This over here, you would have to then factor it and then split it up. Okay. Any questions on polynomial long division? All good. Okay. Yes? Sorry, the second? This one. Okay. So here we have x to the 4. Okay, so we're looking at the first one, like your thousands divided by whatever. So x to the 4 divided by x cubed, that's x. Then we multiply. So x times all of that. Let's put this down a bit. Okay, so we've got this x now, from x to the 4 divided by x cubed, this x. X times all of this. So this becomes x to the 4. Times by x, that will be minus x cubed. Times by x, that will be minus x squared. Times by x, that will be plus x. Then we take the difference. So x to the 4 minus x to the 4, 0. And we take the difference, take the difference, take the difference. And now we look at this first term again. That's x cubed. X cubed divided by x cubed is 1. And then we multiply. So 1 times all of this, we just rewrite it. We take the difference. Take the difference, take the difference, take the difference. And we end up with 4x. But this degree, 4x is 1. This degree is 3. We don't need to divide anymore. Because the top degree is 1. The bottom degree is 3. Well, that's what we wanted. We wanted the top degree to be less than the bottom. So we stop there. And whatever that is, that's our remainder. Whatever's at the top, that is our whole number part. Okay. Any other questions? Okay. There are plenty of examples and questions in the coming tutorial. Okay, let's do some integration. So we're going to have the integral of 2x squared minus x plus 4 over x cubed plus 4x. Okay, so what do? First thing, we check if we have to do polynomial long division. The degree of the top is 2, degree at the bottom is 3. 2 is less than 3, so we skip that step. So no polynomial long division. Next step, we try and factor the denominator because we want those individual products at the bottom. Okay. Can this be factored? Yes, we can take a x out. That's fine. So this is going to be 2x squared minus x plus 4 over x cubed plus 4x. We can write this as 2x squared minus x plus 4. Again, the numerator, we're not interested yet. We will do that later. Okay, the bottom, we can factor. We can take out an x. Okay, that is all the factoring we can do. X squared plus 4, we stuck with that. We cannot factor any further. So now we look at cases 1, 2, 3, and 4. X, which case is this? 1. Good. X squared plus 4. Case 3. Yeah, because it's quadratic, we cannot factor it. There's only one of it. So we don't have to do any rectification. So we go to case 1, case 3, we can split it up. So I'm going to write this again. So we're going to have 2x squared minus x plus 4 over x squared plus 4 is equal to, the first one was case 1, so it's going to be some number a over x. The second term was case 3, so it's going to be some linear term bx plus c over x squared plus 4. A, b, and c, we don't know what they are. We need to figure that out. So what can we do? Working with rational functions like this is quite messy. We don't want to do that. So what we do is we clear the denominator. So notice this denominator here has factors here and here. If we multiply by this denominator, these denominators get removed. So let's do that. So we clear out the denominator. We get 2x squared minus x plus 4 is equal to, the x and the x will cancel, so we're left with a x squared plus 4. X squared plus 4 and x squared plus 4 cancel, and we're left with bx plus c times x. Okay, we can simplify this a bit further. So we have 2x squared minus x plus 4 is equal to, we have ax squared, and the second term we have bx squared. So we can write that as a plus b x squared. Then we have a cx, so we can put a plus cx. And lastly, we have a 4a, so we can put a plus 4a. So this is just to make the two sides look more equal. So here we've got some quadratic term with 2. Here we have quadratic with c. Here we have the linear term with minus 1. Here we have the linear term with c. Here we have the constant 4. Here we have the constant 4a. So now we want to solve for a, b, and c. Okay. There are 3 ways that we can do this. I suggest you try out all 3 ways, but pick what works for you. So number 1 is by inspection. So what we do is we eliminate them one by one to see if we can solve them. So the 2 of them we can find right away. Here the coefficient is minus 1. Here the coefficient is c. It's the same term. So c must be minus 1. Okay, so we got one of them. This term is 4. It's the constant term. This constant term is 4a, but they must be the same. So a must be 1. So a is 1. And lastly, we know a is 1 already. So here we have a 2. Here we have a plus b. A is already 1. We know that. So b must also be 1. Okay, so that's by inspection. We can see what to do there. Okay, second method is substituting x values. Okay, so we look at this line over here, and we think to ourselves, what values of x can we substitute to make this easier for us? So let's have a look over here. So what happens if we substitute x equals 0? That will be 0. All of this will be 0. And we're left with 4a. And on this side, this will be 0, this will be 0, and we get 4. So we can substitute x equals 0 to left-hand side and right-hand side. So on the left-hand side, we substitute 0, we get 4. On the other side, we get a times 4. Okay, plus b times 0 plus c, and then all times x, but x is 0. So we get 4 equals 4a, so a equals 1. And then we can then substitute the known value for a. We can substitute it back here, so a is 1. And we can substitute a different value of x. So let's say x is 1. We can substitute x equals 1, and we're going to get some equation for b and c. We can substitute x equals minus 1. We get some equation for b and c, and we can solve. So we can substitute other values like x equals 1, x equals minus 1 to solve for b and c. Okay, you can try that out for homework. So substitute 1, substitute minus 1, and then you'll get a simultaneous equation for b and c. Okay, so you can try that out. Okay, and then step 3 is with a system of linear equations. You've heard that before? Okay, good old math 132. Okay, so what do? We want to take this system of 2 equations here and end up with 3 equations for the 3 unknowns. Okay, you've heard all of that stuff before. So here we've got x squared and x squared. We've got 2 and a plus b. So 2 equals a plus b. That's equation 1. Then we've got minus 1 and c. It's equation 2. And here we've got 4 equals 4a, equation 3. 3 equations, 3 unknowns. You can solve them as a system of equations. So we've got, from the first one, we go back up here. So 2 and a plus b. Okay, then the second one, c and minus 1. So leave some space here. Okay, and lastly, 4a equals 4. Okay. So we've got a system of 3 equations. You know how to solve that from your Math 132 work. This one is very easy to solve. Okay. You know, we got C and A already. You just substitute and you can solve. It won't always be this easy. Okay, so this is just a practice example, but try for the next example, use your Math 132 work to solve for A, B, and C. Okay. Sometimes we'll have A, B, C, D, and E. Solving them simultaneously gets a bit complicated, but solving them as a system of linear equations looks a lot easier. Okay, so just keep that in mind. There are different ways of solving for the coefficients. Please find what works for you. Okay, but either way, we've got our coefficients, whatever method you use. So let's do the integral. Okay, after all of this work, you might forget that we're actually trying to do an integral. Okay, a lot of steps here. So 2x squared minus x plus 4 over x cubed plus 4x. Okay, so finally, after doing all of the polynomial long division, after solving the system of equations, we can now set up the integral. And we're halfway done. Okay, so this is going to be equal to, we know a, b, and c, so we can just substitute. So this will be the integral 1 over x plus x minus 1. Remember, that was the remainder bit that we had. Sorry, not the remainder, that was the second term that we had, over x squared plus 4. Okay. And now we can start with the integral. Okay, so all of that stuff before, that was the pre-stuff. Now we can do the integral. Okay, so what do we want to do? This one, easy, natural log, don't worry about that. This one, a bit more complicated. Can we do a u substitution? If we let u be the bottom, this x squared plus 4, then du is 2x. This top part is x minus 1. That's no good, so we're not going to try that. Next thing, we have x over x squared plus 4. We can do that as one thing. Minus 1 over x squared plus 4. We can do that as another thing. So let's split it up. So we're going to write it as x over x squared plus 4. Minus 1 over x squared plus 4. So with it being together, we couldn't do a u substitution or anything. But now that they split up, we can do that. So let's go through it again. 1 over x, that's the natural log, easy. If we let u be the bottom, du is 2x, that takes care of the top, easy. 1 over x squared plus a squared, that's arctan, easy. If you didn't think any of those were easy, please go back to the previous methods. Okay, at this stage, you should just be putting the answers right away. Okay, so this will be the natural log. This will be 1/2 the natural log of x squared plus 4, and this will be 1/2 arctan x over 2 plus c. Okay, again, big warning. If you cannot go from this step to this step in this one line, you need to go back and review your work from the previous weeks. Okay, again, from here to here. If you cannot do that in one line, like I did here, you need to do more u substitution practice. Going from here to here, you didn't know this was arctan. Go back to your table of integrals. Okay, this is one of the special integrals we did. Okay, so please make sure that you go back and revise your work if you couldn't do that in one line. Okay, again, with the test and the exam, time is not on your side. Okay, if you need to do these steps, as rough work on the back of your page for like 5 minutes, that's way too much time. You're wasting your time on that. Okay, there shouldn't be any side working or rough working or thinking or anything like that. Just question, answer, like we did. All right, any questions on this? All good. Okay, example 2. Integral 1 minus x plus 2x squared minus x cubed all over x into x squared plus 1 squared. Okay, so some things a little bit easier, some things a bit more difficult. So first of all, let's look at the degree of the top and the bottom. That's always the first thing. The top has degree 3. Let's look at the bottom. Here we've got x squared, so that's x to the 4. We've got another x, so that's x to the 5. So the degree of the top is 3, degree of the bottom is 5, so no polynomial long division. That's fine. So no polynomial long division. Okay, remember, I'm not going to tell you if you need polynomial long division. You need to figure it out. Okay, the next thing was factoring. But the bottom is already factored. So that's given to us. That's fine. So no factoring needed. Okay, that's good. So sometimes I will give you questions where it's already factored, That saves you some working. Okay, next, we split it up into its parts. So we look at each term in the bottom, and we see case 1, 2, 3, or 4. So we got 1 minus x plus 2x squared minus x cubed, all divided by x squared plus 1 squared. Okay, and we want to split this up. We've got x, so that's going to be some a over x. Next, we have a quadratic. It cannot be factored. It's already factored enough. It's repeated twice. So we're going to have one term with the quadratic, another term with the quadratic squared. So this will be bx plus c over the quadratic. And then let's say dx plus e over the quadratic squared. And that's it. Yeah, that's the decomposition done. Now we want to solve for a, b, c, d, e. Okay, we've got quite a bit to solve for. Like I said before, we don't want to work with fractions, so let's clear the denominator. So we're going to have 1 minus x plus 2x squared minus x cubed is equal to a over x times all of that there. That's going to be a x squared plus 1 squared. Then we have the next term, x squared plus 1. That cancels with one of the x squared plus 1s here. So that's going to be bx plus c, x squared plus 1. Okay, one of them got cancelled. And then the next one, x squared plus 1 squared. That cancels with this x squared plus 1 squared. We're left with x. So plus dx plus e times x. Okay, and now we have this equation to solve, right? For a, b, c, d, and e. Now there's a number of ways you can do this. So let's go through them. So the first way is by inspection. Can we do this by inspection? No, it's a bit complicated, so that's not going to work out. The next thing we could do is multiply everything out. So this whole right-hand side here, we multiply it all out so that we get the cubic terms, quadratic terms, linear terms, constant terms, and then we compare the coefficients. You can either do that by inspection, like we did before, or you set up your system of equations. Okay, I'm not going to tell you which way to do. You can find the best way for you. So homework, try that out. Okay. So maybe substituting x equals 0, that could help quite a bit. So you can always do like a bit of a mix. So if we substitute x equals 0, this goes away, this goes away, and this is just a. This goes away, this goes away, this goes away. We're left with 1. So a equals 1. We know that already. Yeah. And then you can figure out the other ones as well. Okay, so we got a equals 1. So we did that by inspection, just by substituting x equals 0. The other ones, okay, it might be a bit more difficult. Try that out. But you should get b equals minus 1, c equals minus 1, d equals 1, and e equals 0. Okay, so try it out with those different ways we went through. You should get these answers. Okay, but let's get back to the integral. So we have the integral. A, we know, B, C, D, E. We all know that, so we can substitute and then figure out the integration. So we have 1 over x plus B is minus 1, C is minus 1. So we're going to have minus x minus 1 over x squared plus 1. D is 1 and E is 0, so we can leave that out. So that's going to be plus x over x squared plus 1 squared. Okay, let's go through it. First term, 1 over x, that's the natural log, easy. This one over here, if we let u be the bottom, then du is 2x. We can't do that. We're going to have to split this up. This one over here, if we let u be x squared plus 1, du is 2x, you've got x, easy. Okay, so let's split up that middle term, and then we can write down the answers. So it will be minus x over x squared plus 1, minus 1 over x squared plus 1, and x over x squared plus 1 squared. Okay, let's go through them again. So 1 over x, that's natural log, easy. If we let u be x squared plus 1, du will be 2x. We can take care of that, easy. This is arctan of x, easy. If we let u be x squared, du is 2x. That takes care of the top, easy. Okay, so nothing complicated now. We can just put down the answers. So this will be natural log of x. This will be half natural log of x squared plus 1. This will be arctan of x. And this will be minus 1 over 2 x squared plus 1 plus c. Okay, again, once you get to that last step, each individual integral should be very easy to do. So in the beginning, it looks very complicated, do a lot of work, but in the end, it's very easy to do. So it's either some natural log, like these ones, it's either going to look like this, when you have an arctan, or it will be something like 1 over u squared, like with this one. It won't be any more complicated than that. Okay, so there's no natural logs, there's no exponentials, there's no trig functions. It's just like we have here. Okay, 1 over x, or 1 over u squared, arctan, logs, those simple ones. All right, any questions on this example? Oh, good. Okay. Okay, so just go through this again for homework, and then just make sure you can fill in these missing steps here. This that homework step there. Okay, fill that in. Okay. Any questions on what we've done today? No. Okay. So we'll leave it at that for today. For tomorrow, please do some textbook reading. Textbook reading. So this is the chapter on partial fraction decomposition. Okay, it's just after the trig substitution chapter that we did last week. And then please read, it's a very small little sub-chapter on rationalizing substitution. Okay, very small chapter, but please read that for tomorrow. If you do want to start with the tutorial work, there are some questions on this rationalizing substitution. You can try them out. But the rest of the tutorial, you should now be able to complete. Okay. So the tutorial questions will be something like this. Okay. It is either factored for you, where you can just split it up. Other times you will need to do the factoring yourself. And then the third case is if you need to do some polynomial long division first. Okay. I think the tutorial does tell you what to do, but for tests and so on, I'm not going to tell you the steps. Okay, you need to be able to go through the steps. So that's step 1, long division, factoring, splitting it up, solving, and then integrating. Okay, please make sure you can follow those steps. Okay, tomorrow we're going to do the small bits on rationalizing substitution. Please read that before the lecture. Okay, any questions? No. Okay.